Okay, hi everyone. So today we're going to talk about what we call instantaneous rate of change. Instantaneous. Let's go right. Instantaneous, I think, huh? Instantaneous rate of change. I always have problems spelling that word. Instantaneous. That's how you spell it. Rate of change. Now, what is instantaneous rate of change? It's the change at that very moment. Let's talk about a graph here. If I give you guys a graph, and let's call this, make it look like a roller coaster. The world is a roller coaster. Okay, so what happens? What is the slope? What is the slope looking like here? Now, at the peak of a graph, let me go ahead and change this right here to a different color. At the peak of a graph, like right here, the slope is not really moving. Right at this point right here, am I really going anywhere? Think of the top of a roller coaster. You stop for a very brief moment, don't you? And then as the roller coaster starts to tip over, you start to change even faster, right? So the slope gets worse and worse and worse. These lines become even more deeper. And by the time you hit the ground, you're at their fastest speed possible. So this instantaneous rate of change isn't what your overall average rate. The average rate is from the top to the bottom. That's our average rate of change. Our instantaneous rate of change is really at this very moment, what is going on? At this very moment here, what is going on? At this very moment here, what's going on? What does the slope look like? Oh, sorry. So the instantaneous rate of change is us trying to figure out what is the slope of the graph, not at two different points, but at one point. Now let's talk about slope before when we saw this. Before we had the graph that looks something like this, I say, if I want to find the slope between 2 points, you just take the 2 points, and then we use the equation m is equal to f of b minus f of a over b minus a. Are you guys okay with that idea of slope? But the problem with slope, looking at 2 points, is it makes this secant line here, where you end up with 2 lines, and this slope isn't really this slope. It's actually a combination of both those slopes. So it's like, in order to find out how fast I'm changing, you have to compare it to something. But if you compare it to something that's too far away, it's not accurate anymore. So how do we deal with this part of things being too far away? If I pick a point that's closer, okay? If I pick a point that's closer, will this make it a little bit more accurate? Yeah, that makes it a little bit better. Pick a point a little closer, even better. Now, our issue is, again, let me go ahead and demonstrate what we're trying to do here. We're trying to find slope, usually using 2 points. Now, for a straight line, that's always going to be the same. If I give you a straight line, let's see, y is equal to 2x plus 1. Here's my 1. Rise up to 1, 2 over 1. The slope of the line is always the same. Rise, over run, rise, over run, rise. Okay, it's always the same slope. But what happens is once we end up with a graph that's curved, depending on which 2 points you pick, gives you totally different slopes. So what that means is I can't tell you necessarily with good accuracy what my change is, how slopey this is, how slopey is this, unless if I pick a point that's really darn close, right? So if I pick a point in the back, over here, oops, come on. Sorry, I forgot my iPad at home today. So if I pick a point over here, so it all depends on who you're listening to. Sure, you might be here, but if you're listening to people too far away, they don't really know who you are. And only as you get closer can you start to realize who you really are. Like people around your house know who you are. But your friends that see you once a week, they kind of know who you are, but not really well. And if you have a pen pal on the other side of the planet, they don't know who you are at all. Just whoever you tell them you are. So here is our goal. We're going to try to get 2 points not far away, but so close that they're right next to each other. Now, if we were in class, we would be able to explain this a little bit better, but that's fine. Especially if I don't have my tablet today, so I'm using the school computer. So it's kind of messing me up. Okay, let's go ahead and look at it. So our equation here is for slope. We could describe it as f of b minus f of a over b minus a. But instead, we described it as a slightly different way. We said f of x plus h minus f of x over x plus h minus x, which gave us f of x plus h minus f of x all over h. And this is something that we worked out on IXL, is that we described 2 points instead of actually using saying x is 1 and x is 3, we said x is 1 and h is 2 steps over. So h would lead us to 3. Okay, so instead of using 2 different letters, A and B, we're going to use 1 point and then use an h in between. And we did this the other day when we were trying to find out slopes. Now what we did is, for instance, if I give you, if f of x, we said if f of x equal to, let's say x squared, and we want x to become 3. And we say, okay, what is the slope, or what can we do with this equation? F of x plus h minus f of x over h was rewritten as x plus h squared minus x all x squared over h. And you remember in the IXL, when you multiply this out, you ended up with something like x squared plus 2, oh my goodness, x squared plus 2xh plus h squared minus x squared all over h. So we multiply that out. You should realize that we have like terms. Darn it. We have x squares. We can cancel those out. And I made a big point on the last lesson to say, when you cancel stuff out, you should end up with just h's on top. Lucky for us, we can cancel those h's out. We said 2x plus h. And this was our slope for the graph. And we went ahead and said, well, hey, if x was 3, if I plug in 3 here, well, for whatever h you want, I can tell you what the slope is going to be. If h is close, great. If h is far, doesn't matter. As long as you tell me how far you want, I can always tell you what that slope is going to be. And we demonstrate this on Desmos to say if h was close and far, you can see what it is. Now, today, we're going to say, how far is your neighbor? How far is that h point? And that h point is going to be so close. Here is our rule, instantaneous rate of change. And we can see the call is also slope. We're going to say the limit as h gets closer to 0 of f of x plus h minus f of x all over h. So this is the formula that we are going to use today to find out what is the instantaneous rate of change. Now, what am I really saying here is that what if those 2 points that you're using to find out slope were not far away, but they're literally on top of each other. They're next door neighbors. They were living in the same freaking house. They're sharing the same freaking bed. Want to know if you're snoring? Ask people to live in your house. So what happens when I do this? Well, here's something kind of cool. We already did all the work. If you can do what we just did in this last section right here, if you can do the work in this section right here, we are done, because here is what we just did. If I say f of x, darn it, come on. If we say f of x equals to x squared, like what we just did in the last problem, this is what we just did in the last problem, okay? Then we said the inside part becomes sorry, this becomes right here 2xh. So the limit is the limit as h gets closer to 0. Oh, this answer was just 2xh. 2x plus h. We just plug in 0, 2x. This equation is the slope at any one point in this graph. Not only do we say it's 2x, if you just told me the x is, like we just said in the last problem, is 3, we plug in 3, the slope is going to be 6. I can tell you what the rate of change is at that one point. Now this means this is kind of a lot of stuff. There's a lot of big ideas floating around. So let's go ahead and do this again. And let's re-explain this. Okay. So how do we talk about slope? Slope is written as f of b minus f of a over b minus a. We need 2 points. Okay, that's how we learned about slope in Algebra 1. And when you are given 2 points on a graph, slope is pretty easy. If I give you a graph, whatever the graph looks like, oh my goodness. If I give you 2 points on the graph, let's say we start here, depending on what point I give you, they give you totally different slopes, right? This is a slope, this is a slope, this is a slope. Great, those are slopes. Those are average rates of change. If I want to get from point A to point B, hey, was I growing? So I need to make some money. And how fast do I have to make it? Not that much. If I take this point to this point over here, I'm losing money. Okay, how fast are you losing? On average, we're losing some amount. And that's the idea of slope. Are you increasing or decreasing? But none of these tell me how much I'm losing at this one specific spot. At this spot here, how much am I losing? If we look at the problem again, sorry, I got wiped out. No. At my point right here, what is the actual slope? Am I losing money or gaining money? If this was a roller coaster, am I going up or going down? If this was a roller coaster, would I be going up quickly or down quickly? And the idea of a slope is how fast something is changing. And that's important for us because we can apply this to a lot of different things in physics, but at what speed is this line changing? At what speed is this line changing? And you guys can see that, do you see how this is actually the tangent line? And is that pretty negative? It is pretty negative. Now using this equation here, I need 2 points, but if I pick any 2 points, it's too far away. And none of these lines, take a look here, you tell me, looking here, do any of these lines here, darn it, shoot. None of these lines here actually accurately reflect the red line that I've drawn. So in calculus, we cheat. We say, hey, how far is the second point? It is h away. Well, how far is h then? Well, h is going to be 0. So let's go ahead and practice this, what I'm talking about, with a problem. If I give you f of x is equal to 3x plus 2. Can you guys tell me right now what the slope of this graph is? 3x plus 2. Hopefully you see this is a line equation. So our slope is automatically 3. How do you know that? You know that because you memorized this from Algebra 1, right? Also, if you're good with number sense, this graph is changing 3 steps every single time I move. If I plug in 1, that's going to be 3 times 1 plus 2 is 5. But if I plug in 2, it's 3 times 2 plus 2 is 8. If I plug in 3, 3 times 3 plus 2 is 11. So I'm changing by 3 times every single time. That's slope. It's changing at a constant rate like a regular line would. All right. So when I do that, we know the slope is 3. But could I do this with two different points? Well, yeah. Let's take 1, 5 and 11, comma 3. Where did I get these numbers? Right here. Would this still give us, whoops, I wrote it the wrong way. 3, comma 11, sorry. Would this give us the same slope? Well, yeah, rise 11 minus 5 over 3 minus 1. This gives us 6 over 2, which is 3. Hey, that's the same slope. We went through slope 3 different ways already. Now, if we look at this from the calculus approach, because the idea of calculus, it allows us to solve problems that are, of course, are not obviously true. It can give us harder problems, and we can do the same process on these harder problems instead of trying to guess our way through it. Because for a line, this is so predictable. We know what it's going to be. But let me go ahead and let's do the calculus approach. It's the limit as h approaches 0 of our new point minus our old point all over h. I tried to make a stressful point last time that this is another way of writing slope. This is f of b minus f of a over b minus a. Okay? If a was x and b was x plus h, this is f of b minus f of a. Take a look. This is your b, this is your a. That's what we were copying. On the bottom, if it's b minus a, that's x plus h minus x. The x's cancel out, leaving me just an h. This is just the equation for slope. Now, I'm going to show you guys really quickly how can we plug this in. And it's straight brainless work. You just plug it in. F of x, we said was, reminder, f of x is 3x plus 2. So in the problem, I'm going to write 3x plus 2 minus 3x plus 2. What is my x? Take a look here. I'm going to plug in x plus h in the front, and I'm plugging x in the back, all over h. And this is the step that we did last time. I did forget one step. I need to remember to always remember to write the limit as h gets closer to 0. You're going to have to plug in the limit every single time in all these steps. Equals to, let's go ahead and multiply the limit as h gets closer to 0. Let's distribute the 3 here. Distribute the 3. 3 times x is 3x. 3 times h is 3h. Plus 2. Negative times a positive is negative 3x. Negative times a positive is negative 2 all over h. You might say, Mr. Cole, that seems like a lot of work. Really? I just multiplied the 3's. Let's go ahead and get rid of our like terms. I have 3x and 3x. I have 2 and 2, exactly what we did last time. We end up with a limit, h gets closer to 0, of 3h over h. Oh, lucky for us, we can divide the h's out now. Like exactly what we said last time, we want to make sure we cancel out the h's. We're left with the answer, the limit, as h gets closer to 0 of 3. Hey, there are no h's left. The answer is just 3. What does 3 mean? 3 is the slope. Okay, that looks terrible, but that's the slope. 3 is our slope. And we came up with the answer. 3 is the slope regardless of what situation we're in, no matter how far h is. If h is 0, if h is bumped up right against that line, okay, we're doing literally the impossible here. You can't find slope with only one point, but that's why we use limits. We don't say what is it, we say what should it look like? What would it look like if those 2 points for slope were just actually the same point? What would that look like? And that's what we do here. Let's give you guys another example of what we're doing here as we practice this. If the problem was if f of x is equal to 3x squared plus 2. Take a look here, folks. 3x squared plus 2, that looks like what we did before, except what is the type of graph is x squared? Is that still a line? And for this graph, this is a parabola, 1, 2, and going up like that. Now this is a fast changing graph, and any 2 points that you pick, you're not going to get an instantaneous rate of change. You're going to get an average rate of change. So why do we call it average? It's because if I pick, let's go ahead and pick 2 points. Let's pick a point here and pick a point here. So on average, didn't we make money? So we didn't make money here. We were losing money. We were in the pits. This is like buying a GameStop. We were losing money. But eventually, doesn't this graph start to pick up? And as it starts picking up, so does my average. So that's our issue here. We're trying to figure out what not the overall rate of changes, but what is our instantaneous. Oh, they crashed it. Good job, Mr. Code. You crashed it. All right, so the problem is if I pick 2 points, it would never give us our instant rate of change. And what I mean by instantaneous rate of change means exactly at one point. If I ask you for this point right here, what is the slope? Is the slope going to be up or down? And the slope is represented by the tangent line. If I could draw a line here, would that slope be positive or negative? The slope would be negative. But if I draw a slope on the right side here, that would be positive. So it depends on where you pick your point, what our slope would look like. So we're going to come up with a general equation for that. And then we're going to figure out what is the slope at x equals 2. That's to put it as x equals 2. Oh, don't freeze. What's the slope at? Oh my gosh, you are going to die. Oh my goodness. This guy. Where are you? Best video ever, Mr. Co. This should have been it. Nope. Oh, so frustrating. Okay, let me redo it. So we're going to take our derivative of this guy. We're going to find the slope, instantaneous rate of change, by just following our limit rules. We always just write the idea of limit. The limit as h gets closer to 0 of f of x plus h minus f of x all over h. Okay, we said we're going to do this as x equals to, we'll say x equals to 1. Okay, what does the slope look like at x equals to 1? So at 1 right here, what does the slope look like? It looks like it's going to be positive on the graph. So let's go ahead and say the limit as h gets closer to 0. And then we're just going to copy this function f twice. 3x squared plus 2 minus 3x squared plus 2. And this, I'm going to leave it as blank, sorry. 3x, oh darn it, come on. I wasn't going to write x, I was going to leave it blank. Squared plus 2 all over h. Please, everyone, I want you guys to make note that these are exactly the same equation. Why? Because they're both f. The only difference, just like random flavored filled donuts, you guys ever get a donut, like your family bring home a donut and you're not sure what the creamy filling is till you take a bite out of it? Yeah, the filling changes. That's all that changes here. In the front, we're going to have to write x plus h. And in the back, we're just going to write x. Why do we have these two different equations? It's because, remember how we have two y's, y2 minus y1? They're both y's. They're just different x values plugged in. This has my upgraded one in the front, and this has my old one in the back. Now, what we have to do is we have to practice our algebra 2 skill now. We're going to multiply out 3x squared plus h plus 2. We're going to multiply that out. So it's going to be 3 times x squared plus 2xh plus h squared plus 2 minus 3x squared plus 2 all over h. You might say, Mr. Go, that seems like a lot of work. You know what? It could be. But the reason why I was able to do this so quickly, because this is what I want you guys to make sure you guys can see. If I square something, it's always square the front, square the back, and double the middle. And the middle is going to be xh. So I just copied that here. That's where I got this. We're going to go ahead and multiply that out. Oh, I'm running out of space. Shoot. Okay, so we're going to end up with the limit h gets closer to 0 of 3, multiplying the 3 out, 3x squared. 3 times 2 is 6. 3 times h squared is 3. And then minus 3x squared minus 2. Let me ask you, is that a hard step? Is the first step that hard? X plus h. Is the second step, me multiplying out the squared, is this part that hard? Is me multiplying the 3 out that hard? Now, the next step, again, my question is that hard? Can I combine like terms? Oh, I lost the 2. Whoops, I forgot to copy down the 2. Remember how there's a plus 2 here? I forgot to write plus 2. Oh, I forgot about that. So a plus 2 and a plus 2. They're going to cancel each other out. And we are going to be left with only h's. And we did this in IXL last time. We're going to do the same thing here. So we're limit h gets closer to 0 of 6xh plus 3h squared all over h. Now, just like in IXL before, we said we can divide everyone by h. Do you see h's on top? I'm going to divide them all out. Here you go. See you later, h. It was fun while it lasted. Limit h gets closer to 0 of 6x plus 3h. Now, here's what we do. We plug in the 0. 6x is my answer. Now, what does 6x mean? 6x turns out to be the slope, but for every point on the graph. What I mean is, if I look at this graph now, if I put x is 1, remember how x is 1? 6x is my slope. That's the slope equation. You just have to tell me what the x value is. If x is 1, the slope at x equals to 1, the slope is 6 times 1, which is 6. And that's 6 right here. What about if x was negative 1? At x equals to negative 1? Well, it's 6 times negative 1. Hey, it's negative 6. The slope is negative 6 here. What about at 0? 0, okay? 6 times 0 is 0. That's my slope. What if at 2? See how this is actually more slopey over here? 6 times 2 is 12. The slope is 12. So we're able to create an equation that finds all the slopes for all the graph at every point possible. We have literally determined the future. So these are the main two equations you guys are going to be dealing with. So go ahead and work on IXLs. And if you get stuck, we'll talk about it next time I see you. Thank you very much.